Good day, I'm Dr. T and welcome to my office. So today I'd like to talk about the periodic table. Obviously a fairly useful tool as chemists, and one that as a student of chemistry you'll be using a ton. Well, I should say you'll be using a ton sometimes. Honestly, I don't use it all that often because most of what I'm doing, that's just not the tool I need. But of course, when I need it, I need it. But before I start talking about it, I'd like to talk a little bit about its history. Basically, the goal here is to take all of the elements, all of the types of atoms that we know about, and organize them. And of course, we've been doing that since before we knew what atoms and elements were. Since antiquity, you can see lists of, say, the things that the alchemists thought were the building blocks of everything, or potentially, the useful tools that they were using, the useful chemicals that they were working with. Of course, as the Enlightenment kicks off, we start wanting to organize things more scientifically. This newfangled science thing that we've, invented, recently, because of course, we're talking a couple hundred years ago. But there was a small problem with organizing elements. We actually didn't know that many. A lot of atoms, we knew we hadn't figured out there were atoms yet, so of course that was a bit of a stumbling block. But elements in their pure form, we had known some, but a lot of them were kind of difficult to discover. So we were playing with a pretty empty deck. It's not that we weren't playing with a full deck, we weren't even playing with a quarter of it to start with. But as the Enlightenment goes on, as we get in through the 18th century, we start discovering a fairly good chunk of our elements, and really up through the mid-19th century. We've got a decent-sized chunk. We're still not playing with a full deck, but we've got a fair amount figured out. And we start sorting out lists of elements, and we're starting to notice a pattern. If you start listing elements by their atomic weights, at this point we can start getting this idea of relative atomic weight. It's fairly straightforward. Okay, it's not fairly straightforward. It's actually a lot of work to get this information. But we do have this tool. So we notice there's some interesting patterns. As the weight goes up, if you start listing them in order, all of a sudden you start realizing that, almost like musical notes, you kind of get this weird octet. It's not a perfect octet. There's definitely changes and spots where it kind of flattens out, especially with a bunch of these metals. But you get this repeating pattern, what we call periodicity. So we're starting to work on new lists of elements, potentially showing this periodicity, because we notice that there's certain chemical properties that just repeat themselves. If I look at, say, chlorine and bromine and iodine, they actually have very similar chemical properties. There's this bit of a repeating pattern. If I look at things like lithium, sodium, potassium, once again, very repeating patterns as to their chemical properties. So it would be nice to be able to not just have a list, but have a list that can help me explain and predict the chemical properties. And a few attempts get made, and there's definitely some pretty meaningful ones taking place. The classic one to bring out, of course, is by Mendeleev. And Metalloids is this Russian guy. His comes from a poor family. His father, I believe, either died or left them young. His mother really sacrificed to get him an education. He's in Russia, which at the time is not exactly the center of learning. It was a bit of a backwater, to be honest. Goes to college, studies chemistry, and he starts setting to the task of sorting out a list of all known elements. And he realizes, and this is of course in the mid-19th century, that we've discovered a lot of elements in the last 100 years or so. A few hundred years before that, we were talking about a handful of elements. Some of your common metals, a few others, but we've really, at this point in history, discovered a lot. We've really expanded. And he makes this really important revelation. Something that's kind of those life lessons that we all need to keep in mind, even if it has nothing to do with chemistry. That if you've just discovered a bunch of stuff that you hadn't previously known existed, why do you think you know everything at this point? Why do you think you haven't discovered everything? maybe there's something hidden. Maybe there you have yet to get to. Something new, something maybe wonderful, maybe horrible, maybe just different to discover. So he realizes that he's not playing with a full deck. So he takes the elements and actually uses cards, puts the chemical symbol, the chemical properties, the physical properties, the atomic mass, which at this point is being defined relative to hydrogen, and puts them on cards and starts shuffling the deck. And then he does something that is one part brilliant, one part insane, but it makes perfect sense when you realize he's playing with an incomplete deck. He leaves holes. He has gaps. Now, of course, to some folks, once he publishes his idea, they're like, this idiot, middle of nowhere, Russia, poor family, what's the guy know? And he's so insane. He has a list of all the elements in the existence, and he has holes in it. Other folks are like, ooh, that's a good idea. Yeah, there's probably gaps in what we know, and there's probably an element that we'll discover later. Now, he takes this a step further, beyond what others had done, and not only does he say that, hey, there's probably some holes, he makes some predictions, particularly about germanium and gallium. He gets the idea that, okay, germanium will be below silicon. Now, of course, he doesn't call it germanium. He calls it proto-silicon. And starts making some predictions about its melting point, its color, its atomic mass, all those kinds of features. And everyone's like, kind of ignores it. About a decade goes by. And then germanium and gallium get discovered. And germanium matches with creepy levels of similarity. We're talking within a few percentage points of the prediction that Mendeleev had made. You leave gaps in your entire list of everything, and people might laugh at you. You predict the future successfully, no one laughs at you. Now, at this point, though, the periodic table still doesn't look anything like the periodic table of today. What you see behind me, or at least part of what you see behind me, and what will almost certainly be flashing somewhere, probably over here, is a much more modern version, kind of a streamlined. We've edited it. So it has a couple of major regions that I'd like to point out. Also a couple interesting quirks to it. And we're talking something that's really only maybe about half a century old. Once again, there's definitely some revisions. We've been improving this. And there are other forms that the periodic table could have taken. And you can go online and find weird periodic tables that are kind of cool, but also kind of impractical. Because, they're three-dimensional and they don't exactly fit in a book. Okay, so periodic table gets its name from this periodicity. If you go counting over and you loop back, you start seeing similar trends. So in the modern periodic table, elements that are in a column, what we call a group, these are going to have very similar chemical properties. There tends to be patterns in the groups, like they'll become more extreme for certain chemical properties or physical properties as they progress up or down the group. But you will get similar chemical and physical properties. So I'd like to talk a little bit about regions of interest on the periodic table. So let's go ahead and take a bit of a tour. Doing kind of a top-down view or kind of a zoomed out, the 30,000 feet, you can look at the periodic table and divide it into two parts. About 2/3 of the periodic table, the 2/3 on the left and lower parts, are what we call metals. These elements are going to have properties that are all relatively similar, although, once again, there's a fair amount of diversity here. These elements are going to be fairly sharing of their electrons. They tend to form these what we call electron seas, so that some of the electrons in one atom will be shared with, say, the whole group. This is going to give us some rather interesting properties. For starters, it gives them a lot of rather interesting electric properties to interact with light. Photons and electrons have to interact for light to do anything, and, well, if you got lots of electrons, you got lots of opportunities. So metals tend to be shiny, and they tend to bounce light back in a somewhat, true fashion. They don't absorb one color or the other all that much. Although, of course, gold and copper are notorious for not doing that. They are yellow metals. Well, copper is more of a reddish color. If you're looking at the periodic table, of course, you've got that dip in the middle. That's what we call the transition metals. That's kind of transitioning between different types of metals and then into the non-metals. You've also got that clump on the bottom, what is traditionally called the rare earths. This really should be just another dip in the middle. This is a somewhat different pattern of electric structure, and you would expect it to be just another dip in the middle. However, this would make a very wide, very narrow periodic table, which doesn't fit well in the textbook. So traditionally, this is pulled out and put underneath the periodic table. It actually makes a lot of sense to do this, though, because the elements within the rare earths, what we call the lanthanides and actinides, because that's the first one of each of those two groups, those tend to have actually very similar chemical properties. So the fact that they're all pulled out separately, even though they're all separate groups, so you would expect them to be significantly different, they're not. So they almost behave like one giant group, even though they're not. There's quite a few different elements in different groups there. Now you look at the periodic table, you see the kind of the block on the right. There's a diagonal line, or an invisible diagonal line, that typically runs between boron and aluminum, and then going kind of in a step pattern. So between silicon and germanium, arsenic and I have to look at my periodic table, antimony, yeah. And kind of the step fashion. This is the dividing point between the metals and the non-metals. And I should really point out that the metal-non-metal distinction is a human distinction. It's an artificial distinction. These are really continuums. So you have things that are more metal-like, more non-metal-like. So the non-metals basically flip everything on its head compared to the metals. Whereas metals are shiny, non-metals are dull. And this is because they will share their electrons only with discrete individuals. So instead of having this large communal electron sea, non-metals typically will share in what we know as a covalent bond, really only with, one pair of electrons is shared between two specific atoms. Obviously, sometimes it, changes that up. Carbon, when it forms graphite or graphene, will create an electron sea of sorts. It's not a true sea, but it's like one. So it does at least become electrically conductive. As that sentence implied, most nonmetals, or basically all nonmetals except for graphite, are insulators. They don't allow electricity to flow through them because the electrons can't really move much, as well as heat doesn't tend to move very well either. Metals, the electrons can move, you can move electrons through it, that's electricity. The heat goes with them kind of scenario. So you can move heat, you can move electricity pretty easy in metals. They're good conductors. The metals can be beat into sheets or pulled into wires, what we call malleability and being ductile. Non-metals, they are brittle. If you try and beat them or pull them into different shapes, they simply crumble. Now, between the two, we usually have a region called the metalloids. So this would be things like silicon, germanium, and elements right on that dividing line. These are ones where, because once again there's a continuum, they kind of are in the middle. So they're not really fitting a classical metallic properties, nor are they a classical non-metal. They're kind of in between the two. Their properties are intermediate. And especially things like silicon and germanium, you can add trace amounts of other elements to kind of nudge them one way or the other. This, is, of course, is the core of how semiconductors work. You're able to take silicon and you can make some of it more metal-y and some of it less metal-y, and you can print, like you would a t-shirt, on your silicon surface, and you can make circuits and electric structures, and since you're printing them, you can make them really tiny, which definitely is useful. Now, at that kind of 30,000 foot, we can zoom in a little bit closer and start looking at a couple of the groups. Remember, groups are going to have similar properties. We already talked about group 1, the alkali metals. They're called alkali metals because when you drop them into water, they tend to react with it. No, they don't tend to. They really do react with it. They remove hydrogen, and what they leave is a base. They raise the pH of the water, which is what we call alkaline. Now, the next group over, group 2, those are the alkaline earth metals. They're not nearly as reactive as the alkali metals, but they're still reactive enough that neither the alkali metals or the alkali earth metals are found in their metallic form in nature. Actually, most metals are not found in their metallic form. They're found as some kind of ionic compound, a salt. They tend to be cations. The alkali earth metals get the name earth into them as an older way of describing they come from minerals. So if you think about calcium and magnesium, these are common things in rocks and soil and whatnot. The transition metals, of course, you got quite a few interesting metals there. I usually like to focus on group 11, what's called the coinage metals. Most books won't throw this in because it doesn't quite hit high enough on their interest category, but I do like to point this out. Because this group, unlike most metals, is sufficiently low in its reactivity that you will find these metals in their metallic form. And these are going to be copper, silver, and gold. So you can go out into nature and find a copper nugget, or a silver nugget, or a gold nugget. And of course people have, and these are usually highly valued because, hey, they're shiny, they've got good electrical properties, and they're useful things. Of course, some are more valued for their usefulness, and others are more valued for their, ooh, shiny. Look at you, gold. Now, you've got a bunch of your large, what we call the P block, and that will make a little bit more sense when we start talking about electric structure of that next block on the side. Going over to our last two groups, the group 17, what we call the halogens, that's going to be fluorine, chlorine, bromine, iodine, and actinium. Actinium, there's only like a gram of it on the planet. It's radioactive. It doesn't have a particularly long half-life, so the amount of research into it is a bit flaky, to say the least, because there really isn't much to work with. But the other ones are quite well known. We use them quite a bit. These are called the halogens. They tend to be fairly chemically reactive as well, but these are non-metals in this case. They tend to form anions, which are going to be, once again, things with a -1 charge. And in this case, they do so quite readily. They like to take an electron from somebody else. When they're in their elemental form, though, they are diatomic either gases, or in the case of bromine, it's a liquid. Iodine, it's a solid, albeit both of which are quite volatile, so you can get them into a gas fairly readily. The last group on the periodic table was actually one of the last groups discovered as the noble gases. Noble gases are, as their name suggests, gases. They get the term noble because they typically are extremely non-reactive. With the exception of xenon, you basically don't get any compounds made with these. And even xenon, reacting with fluorine is a fairly difficult prospect. These were some of the last elements discovered, or this was the last major group discovered, because they're so hard to detect, because they don't do anything. It's hard to detect something that just sits there. Helium was actually discovered on the sun from the solar spectrum before it was discovered on Earth. Just because, once again, it's so just sitting there. It doesn't really do much, and it's also relatively rare on Earth.